This video will be an introduction and motivation for the first design lab in aerospace, ASEN 2002, Thermodynamics and Aerodynamics, on atmospheric satellites. I'm your host, Bobby Hodgkinson. Let's jump in. This lab is a multi-week, multi-month lab assigned today, Wednesday, the 26th of August. The presentation will be due at 8 a.m. on October 14th. That presentation is a 15-minute recorded presentation that you'll work on with your group members. The midpoint status quiz will be due September 23rd, 2020. The details of that will be presented later on as we get closer to the midpoint quiz. And also there will be an individual quiz at the end of the lab that will be due after the lab submission has been completed. Here's a week-by-week look at the lab activities. I highly encourage you to finish this lab presentation early on, ideally in week 7. Pay attention to your overall course schedule because week 8 there's also a midterm exam for thermodynamics. Do not wait to the last minute to start working on the presentation, and the schedule has been set up for you to easily complete all lab activities in week 7 ahead of time to give you adequate preparation for the thermodynamics midterm exam. We're going to be following the design process, which you've been exposed to in freshman projects. You'll also be exposed to this more in 2001. We're going to be developing models for these atmospheric satellites, these balloons, if you will, in accordance with the design cycle. We're going to use the applied model and the development of models to help us walk through this design cycle. More information on that will be presented in following videos. You'll also be getting more exposure to the design cycle and modeling in 2001. We're going to look at models from a slightly different lens than you will in 2001 with Professor Wingate and Johnson, but the principles are going to be very similar. So here's some examples of similar balloons to the one that you will be designing in your group. Google's Project Loon uses a network of balloons to establish connectivity to remote underserved areas, such as those in remote sub-Saharan Africa. These balloons are able to stay in the stratosphere 60,000 to 75,000 feet above the ground level for hundreds of days. The speeds that Google's Project Loon is able to achieve are comparable to 4G LTE. These balloons are solar powered during the day and carry large batteries to provide connectivity at night. Google's Project Loon recently eclipsed over 1 million hours of flight time on their balloons since 2013. The project has also completed over 1,750 launches since its inception in 2013, with over 250 launches in 2019 alone. The record for duration for one of their balloons is over 300 days of continuous flight time. Space Perspective is a company out of Florida that's taking a different view for balloons in the high atmosphere. Space Perspective is planning to launch up to 8 passengers and 1 pilot on its spaceship Neptune. These tourists will spend upwards of $125,000 per seat to get a view of the Earth from over 100,000 feet for 2 hours. If you have that kind of money, maybe we should talk about something different. Interestingly enough, Spaceship Neptune does not use helium as their lifting gas, as there's a worldwide shortage of helium and it's become a very expensive commodity. Instead, Spaceship Perspective is planning to use hydrogen as the main lifting gas for their space tourist balloon. You may recall the Bull Stratos jump back in 2012, in October of 2012, where Felix Baumgartner jumped, really just fell, from an altitude of over 24 miles. Felix was able to reach a top speed of over 843 miles per hour, which equates to around Mach 1.25. Following the Bull Stratos jump, a Google executive, Alan Eustace, jumped out of a balloon so that he could establish the world record for the highest free fall from a balloon. This activity is showcased on a Netflix show, 14 Minutes from Earth, that I've watched, and I definitely encourage you to watch it if these balloon launches are something that are very interesting to you. Wikipedia states that the jump's altitude was 135,889.108 feet. Now, Wikipedia apparently isn't very good at significant figures. You're going to be exposed to this concept of significant figures and the meaning that numbers have later on throughout the semester. 0.001 feet is about the width of 4 human hairs. The concept of significant figures would tell Wikipedia that we should not report the altitude of something that's over 135,000 feet to the width of 4 hairs. There's simply no way that they could be that accurate or that precise with the altitude measurement. Come on, Wikipedia, you can do better. Some recent balloons from the CU Boulder Aerospace Engineering Department. One of the projects was named HALO, the High Altitude Lifting Orbiter. HALO will create an autonomous tethered payload system capable of orbiting outside a balloon's wake. A control surface will be used to induce oscillations. Basically, they had a wing following a balloon as it traversed up into the upper atmosphere, and the wing circled the balloon to take pressure readings outside of the balloon's wake to get an idea of the conditions high above the Earth's surface. Another project from last year's senior project was WORMS, the weather balloon infrared readings of moisture in soil. WORMS had a balloon tethered about 30 feet above the soil with a camera that was reading in the IR spectrum, looking down on the ground to measure soil moisture at different locations in the camera's viewpoint. There's also an ongoing research project with Dr. Lawrence and Dr. Argro to make in situ stratospheric turbulence measurements with weather balloons and to develop the instruments associated with making those complicated measurements. So here's a look at the specifics for your design. In your group, you're going to perform a design for a balloon capable of carrying a payload given the requirements specified below. Now your group will decide whether the payload is a research instrument or human beings or something else. The balloon shall be capable of lifting 500 kilograms to an altitude of 25 kilometers plus or minus 1 kilometer and stay at that altitude for 1 full day. The safety factor for the balloon system will need to be consistent with those of relevant balloons that you will find information during your research phase of this project. We're going to make a couple assumptions here to make this design a little bit easier and more feasible in the next 7 weeks. The first is that we're going to assume that the geometry of the balloon takes on a perfect sphere at altitude. We're going to ignore the transient effects from getting the balloon from the ground up to the high altitude. So essentially, your balloon will just magically appear at 25 kilometers. You'll get to pick the time of day, and then you're going to prove mathematically with the principles that we'll discuss in following videos and that will be discussed in lecture, that this balloon will stay in residence for 1 full day given some other constraints. We're going to allow you to ignore the stresses associated with attaching the payload mechanism to the balloon. Essentially, you can think that that part of the project will be taken on by a different subsystem. You can also assume that the payload mass of 500 kilograms encompasses all necessary aspects for the payload. For example, if you choose to design a system that's capable of lifting human beings, the 500 kilograms takes into account the mass of the humans as well as any necessary mass for the supporting structure and any life support systems that these human beings need. Likewise, for a research instrument, any surrounding materials necessary to keep this research instrument operational are included in the 500 kilogram mass. So a closer look at specific tasks. You're going to be working week 1, the rest of this week, on your own. The groups have not yet been defined. We're still in the process of that. But this week will give you an opportunity in reviewing the material presented here today and in the lab assignment on your own will allow you to contribute more intensely and more in depth with your team members when you get assigned that in week 2. This way, everybody on your team should come in to week 2 fully prepared and fully understanding of the material that's been presented so far in the lab assignment as well as this video. So your tasks are to read the lab document, understand the primary objectives, begin researching high altitude balloons. So you can start with the balloons that I mentioned here today, the Google Project Loon, the Red Bull Stratos, some of the balloons at CU, the Allen Eustace jump, you can begin looking at those balloons. Pay attention to the materials, pay attention to the sizes, the lifting gas. Different information that you think is going to be important for the design of your balloon is your main task when it comes to research. Record the materials, record the lifting gas. Record your findings in a Google Doc, in a notebook, somewhere else that you can refer back to those when you get with your team members in 2 weeks, and then also somewhere that you can refer to those pieces of information when you start developing your presentation in weeks 4, 5, and 6. An additional task for week 1 is to fill out the form that's going to allow us to create these groups based on specific considerations. These considerations this year take in your comfort level and ability to attend lab either in person or remotely, synchronously or asynchronously. We're going to make an attempt to group individuals together that are in similar time zone in order to aid in group communication and coordination efforts. Likewise, we'll release the seating chart such that team members in groups are located in close proximity to each other in the different rooms that we'll be in for in-person activities. This should allow for easier communication and coordination of those individuals while doing in-person activities. With all of that said, communication and coordination amongst your team is absolutely critical now in all group activities, but especially now that most of your work will be done remotely. Looking ahead at week 2, organize your team. Discuss some of these topics as well as other topics that your group comes up with that are going to be necessary to proceed with the remainder of this lab activity. So talk about what do you view as the primary objectives? What are the primary activities that need to happen? So who will be in charge of what activities? Keep in mind that everybody needs to speak during the presentation, and more so, everybody needs to be familiar with the different topics, the different aspects, the different objectives of this lab activity for the quizzes. Discuss amongst your team how you'll communicate with each other. Are you going to communicate over text message? Are you going to communicate over Slack? Are you going to communicate over Twitter after you follow at bhodge6? Will you communicate with each other over Zoom? Will you communicate with each other over a different platform? What time of day and what days of the week work best for you and your team members to communicate and to coordinate and to work on this activity? Now, be aware that people's schedules will change, but in general, you should exchange that information pretty early on in the process so that you can begin working on this lab early and keep up with the activities. In week 2, we'll have a fundamentals video posted, so watch that ideally ahead of time. Come to your group with questions on that video, clarification points, and be ready to start some of the derivations using the theoretical information that's presented in that video. Begin to formulate and understand the governing physics, the governing equations that will define how this balloon size relates to different important parameters such as material, lifting gas, and payload. In week 2 or 3, we'll also have the opportunity for those of you that feel comfortable attending lab in person to participate in a similar scale model experiment. Participation in this scale model experiment is not fully required, as the scale model video and accompanying data are absolutely all that's necessary in order for you to gain the understanding and the primary learning objectives associated with the scale model experiment.